Okay, so in this lesson, lesson 3.1, solving quadratic equations by taking square roots, we're going to, again, revisit this idea of solving simple quadratic equations using square roots. Now we've talked about how you can solve quadratics by graphing. So we could take something like this quadratic x squared equals 16, and we could solve it by graphing. Like we could graph the basic family or parent function quadratic, and you could graph that on the coordinate plane, and then you could graph a line at 16, and you could see where they intersect, much like we did with the absolute value equations when we solved. And it would look like this, and you can see there that these graphs, they cross at up here at -4 and here at +4. So that is one way. Another way we could look at this is by using some simple factoring patterns. And you may remember a simple factoring pattern called the difference of squares. So if we were to say take and put the x squared and the 16 on the same side, so we'd subtract the 16, and that would leave us with 0 on the other side, as you can see here. So we'd have x squared minus 16 equals 0. And then I could break it down into two binomials that are nearly identical. I get the terms by square rooting the x squared and the 16, which would give me x and 4, and the x squared and the 16, which is x and 4. But then one would be a positive and one would be a negative, and that way when we FOILed it back out, they'd cancel out and they would give us no middle term. And then we could use what's called the zero product property, and we could solve each of these equations that each of these binomials equal to 0, and we could then solve to find out those two solutions. And of course, in this case, again, the solutions would be -4 and +4. And finally, we could solve this by using square roots, which is clearly going to be the easiest method, and especially in this case, when there is no bx term. So we can go straight to taking the square root of both sides. And remember, we always want to consider both the positive and negative version. And since 16 is a perfect square, this would give us a positive and -4 for our solutions. So we can see in a graphic form how there's these two solutions. We can see it by having two different factors in factoring method. And then we can see, because we know there's always two square roots of any positive real number, and we can see that here in this case as well. So here are a couple questions to reflect on, and if you'd like, you could pause the video and you could jot down your answers here to these two questions. Number one, which of the three methods would you use to solve x squared equals 5? Explain and then use the method you decided on to find the solutions. Just kind of commenting on this one, I would definitely, in this case, use taking the square roots method because I don't have to worry about having a coordinate grid to graph on. I know that if I were to try to use this factoring method, this wouldn't work, because if I brought the 5 over, that would be x squared minus 5 equals 0, and 5 is not a perfect square, so then it doesn't work with that difference of squares pattern. And so clearly, method C is the best way for this type. And then what about number 2? Can the equation x squared equals -9 be solved by any of the three methods? Well, if you think about using specifically the x squared method, or the square root method, excuse me, if you were to take the square root of both sides, you would be square rooting a negative number. And in the past, we've always said that that's not possible. Well, we're going to take a look at how we can kind of move into another realm of numbers called the imaginary numbers, where we can then take on questions like this and give solutions. But let's practice a few of these square root equations. So basically, this table here just tells you how we're using the product property to simplify square roots, like we did yesterday. For instance, the square root of 12 can be simplified to a square root of 4 times the square root of 3, giving us a 2 square root of 3. And because we know there's two square roots, this is really plus or minus 2 square root of 3. And we also talked about in the prior lesson that you can use the quotient rule for radicals So say for instance you wanted to split a fraction up and square root the numerator and denominator separately. Like in this case, the square root of 5/9. Well, 5's not a perfect square, but 9 is, so if you split them up, you could go ahead and take the square root of 9 and get that denominator to be 3, and then leave the numerator as that square root of 5 because that's as simple as you can get, and then of course plus or minus. Now sometimes when you're taking a square root of a fraction, and that denominator is not a perfect square, in the case of this particular one, this square root of 2/7, when you do split them up, it really doesn't help you because neither one of those are able to be, taken the square root of because neither one is a perfect square and neither one can be reduced. But in a case like this, it's not okay to leave the square root of 7 on the denominator. The rules are you're just not allowed to have radicals on a denominator. So we have to do this thing called rationalize. And when we rationalize, we basically want to turn the bottom into a perfect square by multiplying that square root of 7 by itself, turning that into the square root of 49, which is then 7. But because we have to do the same thing to the top that we do in the bottom, or we change the value of a fraction, we would also have to multiply the top by the square root of 7, turning that into the square root of 14 over 7. But again, now that would be considered to be in an appropriate form because the radical is only on the top and not on the bottom. So that's called rationalizing a denominator. Let's go ahead and turn the page. And we're going to take a look at just practicing a few of these square root equations. We'll do a couple together, and I'll have you pause the video and try a couple on your own. So example A, 2x squared minus 16 is equal to 0. I'm just going to swing that 16 to the other side by adding it, and that leaves me with 2x squared over here and 16 on the other side. I can divide both sides by 2 to undo that multiplying, giving me x squared is equal to 8. And then of course we can take the square root of both sides. And 8 has a perfect square factor in it. And that perfect square is 4, so I could rewrite this as the square root of 4 times this, which then simplifies down to 2 square root of 2. And of course, we consider both the positive and the negative version. So plus or minus 2 square root of 2 would be our value for x. So in example B, when we bring the 9 to the other side to try to isolate the x squared, we then have to divide both sides by -5, and that makes this positive 9/5 because the two negatives will cancel. And now when I take the square root of both sides, this time when I separate them off and use that quotient rule, I can take the square root of the numerator, and that gives me 3, but, and of course plus or minus, but then the denominator, I can't do anything with this in terms of simplifying the radical, but I cannot leave that in that form because it has a radical in the denominator. So what we'd have to do is multiply the bottom by the exact same radical to then create a perfect square of the square root of 25. And so that turns the denominator then into just 5, and the numerator now, that radical shifts to the numerator, making this plus or minus 3 square root of 5. So here's an opportunity for you to try a couple on your own. So we're going to go ahead and try 3 and 4 as you try questions. So take a moment, pause the video, and turn back in when you're ready to check your answers. Okay, so thanks for giving those a try. Take a look at your answers. And be sure to make a note if you have any questions for when I see you in class. the square root of 26 over 4, which might be more informative if we had that rounded, say, to the nearest decimal. And putting that in my calculator, I can see that's about 1.3 seconds. So it would take the water balloon about 1.3 seconds to get from the top of the building down to where it's 24 feet above the ground. Before I have you pause the video to try 6 and 7, number 6 should say, how long does it take the water balloon described in part B to, and it should say hit the ground. So in other words, you want to know when it's on the ground, and so consider how high it is when it's on the ground, and that should allow you to write an equation that you can solve to find out when it hits the ground. And then also complete number 7, and tune back in to check your answers. Okay, so thanks for giving those two a try. Go ahead and check your answers, and if there's anything you can't figure out and you have any questions, just make a note and we'll talk about it when I see you in class. Okay, so we mentioned earlier about how sometimes we're going to come across these equations that we're trying to end up taking the square root of a negative number. And so maybe back in Algebra 1, possibly, or, maybe they decided they were just going to tell you that that's not possible to take the square root of negative numbers. Maybe when you first started studying square roots, they might have told you, oh, you can only take the square root of positive numbers. And within the real numbers, that is true. There really is no defined real number square root of a negative number. But there are square roots of negative numbers in this imaginary set of numbers. So we're going to take a look at what are imaginary numbers and how they're defined and how we can then use them to solve some of these equations that have negative square roots. So you know that the quadratic equation x squared equals 1 has two real solutions. Of course, it would be positive and negative 1. The equation x squared equals 0 would just have one real solution because 0 has only one square root. And the equation x squared equals negative 1 has no real solutions. But by creating a new type of number called imaginary numbers, mathematicians allowed for solutions of equations like this. Imaginary numbers are square roots of negative numbers. These numbers can all be written in the form of bi, where b is a non-zero real number and I is called the imaginary unit. And it represents the square root of negative 1. So in general, we just define the square root of negative 1 to be this letter I that represents the imaginary unit. Given that I is equal to the square root of negative 1, you could also then conclude that if you squared both sides, I squared would equal negative 1. So that's also a really important fact to remember, that I squared equals negative 1, and that the square root of negative 1 is equal to I. So this means that the square root of any imaginary number is a negative real number. When squaring an imaginary number, we're going to use the power of a product property of exponents to expand that out. And we'll also then use this imaginary unit to take square roots of negative numbers. But first, let's take a look at squaring some of these imaginary numbers. So the directions say to square these imaginary numbers. So in other words, if I wanted to square 5i, it means I want to square 5 and I want to square I. So if I square 5, I get 25. And if I square I just learned that this I squared is negative 1. So that would be negative 25. So you think about going in the reverse of that. If we were to square root instead of square 5i, if we were instead to square root negative 25, that means that the square root of negative 25 would have to be 5i. And what about negative I square root of 2? So if we wanted to square that, the first thing we would do is square the negative I. And of course, when you square anything, it's always going to become positive. So that would actually make I squared. And if we squared the square root of 2, that's simply going to cancel out the square root. And that would leave us with 2 I squared, which again, kind of if you think about working backwards instead of squaring the original negative I squared of 2 to get to I squared, if instead we went the reverse and we said, hey, we're just going to square root 2I squared, then it should be equivalent to that original value. So as you can see, this is the process that we're going to use to take square roots of negative numbers, because we said that I squared was really negative 1. So if we were to replace that I squared with negative 1 here, this would actually make this 2 times negative 1, or negative 2. So in effect, that original value here is actually the square root of negative 2. So go ahead and pause the video, and I want you to try squaring number 9 and number 10, and tune back in to check your answers. Pause the video now. Okay, so thanks for giving those a try. So the answers to those two problems were negative 4 for number 9, and number 10 is negative 1/3. Okay, so we're going to go ahead and take what we just learned there about imaginary numbers, and we're going to put that into practice to solve some of these equations that ask us to take negative square roots. So for instance, in example A, x squared plus 12 is equal to 0. So as I bring that constant term to the other side, it ends up making that positive 12 now negative 12 on the other side. So normally I would have said, oh, I can't do that. I can't take a square root of a negative number, but now we know how to handle that. If we were to just take the square root of negative 12, we could actually rewrite this as the square root of negative 1, which we know to be I, well, technically plus or minus I, and the square root of 4, which is the perfect square in 12, and the square root of 3. Now, these first two terms are actually perfect squares. I know that the square root of negative 1 is I, the square root of 4 is 2, so that's 2I, and again, it's plus or minus, and then square root of 3. Now, sometimes you see people write it like that. Sometimes you'll see them write it like this, plus or minus 2 square root of 3I. And the order really doesn't matter. Sometimes people just kind of do that because since I looks similar to a variable, although it's really not, it's an imaginary number. Sometimes they'll write it like that because that's similarly how we write expressions that use variables. And that would be what's called BI form, which we talked about earlier. So that actually technically is the solution for example A. That is the value that if I were to plug back in and square it and add 12, I'd get 0. And you might pause the video now and try that. Try squaring, just like we just did, 2 square root of 3I, squaring all those, and putting it back in and see if you get 0. And how about this one? So I'm going to go ahead and subtract 11 from both sides, and that's going to give me a negative 5 on the other side. And I'm going to divide both sides by 4, and that's going to leave me with x squared is equal to negative 5/4. And I'm going to take the square root of both sides, and since there's a negative radicand, I know I'm going to have to take the square root, basically write this as the square root of 5/4 and the square root of negative 1. Well, the square root of negative 1 is I, and so I know I can take the square root of that, and because I see that 4 on the denominator is a perfect square, I could then write this as the square root of 5 halves, and I took the square root of 4, and that's 2I, and then of course, just keeping in mind that it's always positive and negative. And so plus or minus the square root of 5 over 2I would be the solution to 4x squared plus 11 equals 6. And again, feel free to put that back in, pause the video, put that back in the original equation, and when you square plus or minus square root of 5 over 2I and multiply it by 4 and add 11, you should get 6. So let's go ahead and set these last two questions as you try problems. And so take a moment, pause the video, try them, and tune back in to check your answers. Okay, so number 11 was pretty easy. It turned out that we had a negative 36, and so not only did we have the perfect square of 36 in there, but also negative 1, because of course that is a perfect square as well. Its square root is I and negative I. So square root of negative 36 is plus or minus 6i. That number 12, though, was a little bit tricky because it ended up being the square root of the quotient of 7 and negative 5. And so, of course, factoring out the square root of negative 1 gave me an I. But then that left me with the square root of 7 over the square root of 5, and I needed to rationalize that denominator because you can't leave the square root of 5 on the denominator. So just simply multiply top and bottom by the square root of 5, making that fraction square root of 35 over 5, and then, of course, the plus or minus and the I. So the solution is plus or minus square root of 35 over 5i. Okay, let's take a look at these final reflection questions and wrap up our lesson. So as this video wraps up, I'd like you to take some time and read through these questions 13 to 16 and elaborate on what your thinking is based on the things that you've learned and the things that you know about quadratic functions. To these questions, number 13, the quadratic equation 4x squared plus 32 equals 0 and 4x squared minus 32 equals 0 differ only by the sign of the constant term. Without actually solving the equation, what can you say about the relationship between their solutions? So think about what you kind of already can tell based on what you know about how the square roots work when we have a positive number and a negative number. 14. What kind of a number is the square root, or the square of an imaginary number? So what kind of numbers did we always get when we squared imaginary numbers? Kind of look back maybe at your notes to see. 15. Why do you reject negative values of t when solving equations based on the models for a falling object near the Earth's surface? And think about that. That means, what does t mean, and why would we reject negative values there? And finally, essential questions. Describe how to find the square root of a negative number. So kind of see if you can put that process that we just used in taking the square root of a negative number and just put that in your own words. That would maybe really kind of help you as you come back to try that in future problems, to kind of have a strategy, a process that you use. So that does it for the lesson today. Thanks for coming to class.